What is the principle of a band gap? We have arrived to the question, how do molecular bonds determine the band gap? We have discussed that the silicon atom has 4 outer electrons. These 4 electrons play an important role in making bonds with other atoms in a molecule or in a solid. These electrons are the so-called valence electrons. In a very cruel simplification, a bond can be considered as the mixing of 2 orbitals of neighboring atoms. One valence electron shares its orbital with the orbital of a valence electron of a neighboring atom. This means that it takes 2 valence electrons to make one valence bond. This resulting orbital is called a molecular orbital. From nature, we know that the orientation of a silicon bond is tetrahedral-like. Consider the lattice of crystalline silicon, which is a diamond cubic crystalline lattice. Looking at a single atom in such lattice, the angle between all 4 bonds is 109 degrees. However, if you look at the orbitals of the 4 valence electrons in the third shell of silicon, we don't recognize the tetrahedral coordination. Their shapes do not match a tetrahedral coordination at all. How are these states related to the orbitals? To explain this, we consider 1 electron in the 3s state and 3 electrons in the 3p states. We now make a cocktail of orbitals. We will make these 4 states. In nature, it appears that these 4 states mix into effective 4 symmetric states. The animation demonstrates the mixing. The 4 resultant symmetric states are called the sp3 hybrid. In nature, the 4 valence electrons behave like they are in these 4 sp3 orbitals. The orientation between these 4 orbitals corresponds to the tetrahedral coordination with an angle of 109 degrees between them. Now we can roughly understand the coordination of the lattice of crystalline silicon, but still don't understand the origin of the band gap. For that, we have to look in more detail to how a bond is made between the atoms. Here you see 2 sp3 orbitals of 2 neighboring atoms which are at a far distance from each other. Both orbitals have 1 electron at a discrete energy level that resembles that of the sp3 hybrid. To establish a bond, the 2 atoms have to approach each other. The orbitals start to overlap and merge into 1 molecular orbital with its own shape. Here again, the Pauli exclusion principle starts to play a role. 2 identical electrons cannot occupy the same quantum state simultaneously. Nature splits the original sp3 energy level up in 2 energy levels. The lowest energy level is the bonding level and is lower in energy as the 2 original individual sp3 levels. As a result, both electrons prefer to fill this state in which 1 electron has a spin up and the other electron has a spin down. This bonding state represents the attraction between the silicon atoms and the creation of a bond. The energy level of the bonding level is lower than the original sp3 level and therefore more stable. The second high energy level is called the anti-bonding level. The energy level is higher than the original sp3 level and therefore electrons do not prefer to fill this state. Another important aspect of bonding and anti-bonding levels is that the closer the 2 neighboring atoms are together, the larger the energy splitting between the bonding and anti-bonding level will be. This is demonstrated in the animation next to me. Let's consider the example of silicon again. For silicon, the far majority of electrons will fill up the lowest bonding state. These lower bonding states reflect the valence band as introduced earlier. The anti-bonding states correspond to the conduction band and is hardly occupied by any electrons. The gap between the bonding and the anti-bonding states correspond to the band gap. If you look at the molecular orbital, its bonding and anti-bonding states are discrete energy levels. However, if you look at a solid like crystalline silicon, its network contains many silicon-silicon bonds. All these bonding states do not appear as one single discrete energy level, but spread their energy level continuously over a broad electronic band like the valence or conduction bands. For an insulator, the overlap between the neighboring orbitals is very large, resulting in large energy splitting between the bonding and anti-bonding level, or in other words, in a larger band gap. For semiconductors, the overlap between the neighboring orbitals is moderate, resulting in moderate energy splitting between the bonding and anti-bonding level, or in other words, moderate band gaps. Semiconductors have band gaps which are smaller than 3 electron volt. So far, we have discussed the situation for silicon, which is an element with 4 valence electrons. In the next video, I will extend the molecular description of the band gap to other semiconductor materials like germanium, or 3,5 semiconductor materials like gallium arsenide, or 2,6 semiconductor materials like cadmium telluride. So, see you in the next video lecture.